Very much. Good morning, everyone. I hope you don't mind my English. My Italian is very poor. So I'll do my best to speak slowly, and hopefully what I hope to do this morning is leave you inspired and optimistic and energized to go out and do new things. I heard in my feeble understanding of Italian some discussion about performance-based engineering, and we talk a lot these days about performance-based engineering. And I guess my view these days, having been one of maybe the fathers of promoting performance-based engineering, in fact, what performance-based engineering is real, proper engineering in the old school way. Meaning we use our science, we use our physics, we use our brains, and we think to make good designs, as compared to the prescriptive, follow-the-code approach to formulaic engineering. And so what I hope to share with you this morning is not just some ideas about performance-based engineering, but getting back to thinking about basics, thinking about fundamental principles, and when you do so, you can achieve really miraculous things. So let me launch my show. We're going to talk about things that are changing the world, at least in my view. Before I get into 4 different projects I'm going to present to you this morning, I just give you a brief introduction of my company. We work on many different projects all around the world. I live in Seattle, Washington, where our headquarters is, and from there we do projects in many, many corners of the world, from tall office buildings to airports to sports stadiums, hospitals, libraries, museums, convention centers, and unique structures. All of these are only possible in steel. All of these buildings I just showed were made of steel and could only really be realized through using steel construction. So let me take you on a little journey. I'm going to present 3 specific projects that have been completed and give you a little bit of an insight into, is this okay? Give you a little bit of an insight into the thinking behind them. And then the 4th thing I'm going to share with you is some research that we're currently working on, which I think is the next thing. So the 3 first projects have already been realized, and that was yesterday's thinking. And then I'll share with you some of tomorrow's thinking. So the first project I'll share is the Spheres, which is for Amazon at their headquarters in Seattle. And this project came as the challenge of the chairman of Amazon, Jeff Bezos. He approached the design team and said, I want to create a place where my employees can go and have a nice break, experience nature, and experience a lot of oxygen intake. Because if you're around plants, your brain works better because of all the oxygen from the plants. So he wanted us to create this place, and he challenged us and said, if you think about the historical conservatory, in the sense of the traditional, say, British conservatory, where plants are grown inside, I want to reimagine that with some kind of a new place and a new structure. Don't repeat what has been done before. And so, of course, we looked and studied at all these historical references as inspiration for what might we do different and better. The idea came to us trying to apply very simple principles of geometry. How do we create these spherical structures in something that can be easily rationalized through mathematics? And the ultimate answer for us was this thing, a geometric form. It's called a pentagonal hexacontrahedron. It's a very big word. But essentially what it is a soccer ball with 60 sides, all sides being equal, and each of the panels being a pentagon. And if you make that pentagon 60 equal, identical times, you can make the spherical surface. So this was the basic idea, and the punchline to this entire project is if you have a guiding principle, a big idea that you can formulate your design around, you can create very, very complicated, seemingly complicated structures, but actually made very, very simply. So in the case of applying this pentagonal shape to this sphere, you can see here the beginnings of the idea of how we might create this pentagon 60 times to create the sphere. But the pentagon, in terms of its scale, was quite large. And in order to stabilize that pentagon, we needed to create some kind of a bracing structure inside of it to keep it stable. We studied many, many, many variants of what that bracing structure might be inside the pentagon to keep the stability of the pentagon. Ultimately, we resolved to this combination of engineering, art and architecture, and fabrication. And this was the output of a great collaboration between the architects, the engineers, and the fabricators, looking for a solution that was quite beautiful in the architect's eyes, could be rationalized by the engineers, and then the fabricators could bend and weld and create this piece easily. This was the key to the entire project. If you make this piece over and over and over and over again, you have the structure. At the end of the day, when we made this building, the entire set of structural drawings were only 12. Only 12 drawings to make this building. That's how simple it was. So the fabrication ensued. All of the pieces were made very, very carefully in the shop, pre-assembled and stockpiled. You can see here that they're stockpiled in identical pieces so that it can easily be shipped to the site and assembled. As they arrived to the site, they were lifted in place. You get a little sense of the scale. They're quite large. And as they were put together, the assembly in the field, the actual connections and attachments went together very, very smoothly because of all of the tight tolerances that were available to us via the shop construction and the prefabrication. The ironworkers had virtually no troubles with fit-up or any erection issues during construction. And then when the project was completed, it turns out to be quite beautiful. In fact, I mentioned there's 12 drawings for the entire structure, these 3 spheres that are conjoined. There's 1 drawing for each sphere and 9 drawings for where the spheres conjoin. That's where the complexity was. But the principle to this whole story is that you can make these very beautiful structures very, very simply if you use steel and if you have a big idea that can drive your design thinking. These were completed about 2 or 3 years ago, so if you are able to visit Seattle at some point, please come by to visit. I'll give you a personal tour. It's quite fantastic. Inside, there are 40,000 plants, and these plants were all selected very carefully so that the humidity and temperature control are such that it's a very comfortable place for people to be. As opposed to many conservatories, you go in, it's very humid, it's very warm, it's very uncomfortable. In this particular case, because the charge from Jeff Bezos was to have a place for his employees to go, it was very carefully selected by a botanist to select plants that could survive well in an environment that had a low humidity and a comfortable ambient temperature for people. All right, that's the first project. The second project I want to share with you is a tall building, and the conclusion of this story is through a unique steel construction, we were able to reduce the construction period by 1/3. Not 1 month, 1/3. The construction period for this building was originally thought to be 32 months. We actually completed the building in 22 months. And it was all driven by the structural system I'm going to share with you. So here's the building. It's about 270 meters tall, so fairly tall building, mixed use, and a very slender building. The floor plans for the building are fairly typical of what you might see anywhere in the world. Here in the red color is the core, which ultimately is the structural bracing and structural core of the building. But this is a typical low-rise floor. As the building goes up, it tapers, and the core also reduces in size. And at the top of the building are residential apartments, and the floor plate has gotten much smaller, and the core once again is much smaller. It turns out in this building, because of its height and slenderness, that the core alone was not enough to brace the building for the high winds and high seismic load. And so we also included the idea of outrigger and belt trusses. Nothing unusual about this structural system. This is a system that's been used regularly on buildings around the world. Nothing unusual about it. Also, in the beginning of the project, the idea was to build the building using a technique that's very common, which is a reinforced concrete core surrounded by structural steel floor framing. This is really a tried and true construction approach, but what we also know, having done many of these buildings constructed in this way, is that the schedule of the building is driven by the rate at which the core can be built. You can see one of the issues in this photo, that the jump form for the core is well ahead of the steel erection because the concrete construction is much slower than the steel erection. On most projects that I'm involved in, it's common that the core might advance 1 floor per week, whereas the steel floor framing might advance 2 or even 3 floors per week, much faster. So there's this lag between the concrete construction and the steel, so as they go up the building, the steel ultimately catches the concrete. Our challenge, or our thinking, was how do we solve that problem, or how do we go faster and not have that time lag? And the solution that we came up with was something that we ultimately call speed core. Maybe you've heard of this, but what it is a prefabricated modular panel system wherein steel panels are prefabricated in the shop, trucked to the site, erected like Lego blocks, and then concrete is infilled later. There's no reinforcing steel, no formwork, no embedded plates. It's a very simple system. A simple panel for this system looks something like this. It's 1 story tall. So in the case of our building, it was about 3.5 to 4 meters tall and about 9 to 10 meters long. This is something that could be fabricated in the shop and then trucked to site. If you look down in plan view, it's comprised of 2 steel plates. Each plate is about 12 millimeters thick, so very thin plate, 12 millimeters, 12 meters, and then interconnected by a series of rods or bars or some means to connect the 2 plates together. And a variety of ways that you can affix those rods to the steel plates ultimately was chosen on our project is the detail on the right, where the rods were passed through the plates and then fillet welded on the outside. A second panel type was used compared to the planar panel type, wherein we had doorways that needed to go through the core for elevator lobbies, toilet rooms, mechanical rooms, or what have you. In this case, we wanted to prefabricate all of the coupling beams in the shop as part of the panel system to take all of the coupling beam assembly out of the field and put it in the shop. The field connection from panel to panel as these panels were stacked in the field, in this case, was a welded connection. We have tested both welded and bolted connections. It need not be welded. It could be bolted. In the case of this project, the erector for the project chose to weld because he felt he had greater control over the field tolerance with welding than if it were bolted, and matching up literally thousands of bolt holes frightened him. And so instead he chose to weld. This system was the product of 10 years of prior research. We'd been in the laboratory at Purdue University and at the University of New York in Buffalo testing very large-scale assemblies of this to prove out its ability to withstand temporary loads during construction, its ability to withstand wind and seismic loads. These are our research teams. So we were in the laboratory testing and proving the system worked for 10 years before we found a client who was courageous enough to let us do something nobody had ever done before, and that was to employ the system on their building. A few more bits about how the wall goes together. In this case, what we chose to do was pre-assemble the corners, 8 corner columns, as prefabricated boxes. Those boxes were each 2 stories tall. Those were erected first, and then the panels were swung in between those columns. The erector chose to use this approach so that they could easily erect those 8 columns, get them properly plumbed and true in their locations, and then use them as a guide for these very large wall panels. In addition to the laboratory research, we made very large-scale mock-ups, full-scale mock-ups, in this case to test the concreting operation, because the concreting is actually done later in the field, and we wanted to be sure that the concrete flowed through these walls appropriately, that the material performed properly. We tested everything from concrete strength to modulus to heat of hydration to shrinkage in order to prove to ourselves that the mix design that we were planning to use was going to behave properly. In this case, we made wooden formwork and stripped it away so that we could ensure that the concrete had proper consolidation inside of the core wall after we placed it. We also made a full-scale steel mock-up wherein we prefabricated the pieces in the shop. Here you see one of those corner columns. The circular holes that you see are to allow the concrete to flow around the corner through the column as the concrete's being placed. This is the steel mock-up, allowing the erection crew time to practice. How do we take these very large pieces, very heavy pieces, bring them on the truck, tip them off the truck, hoist them with the crane and put them in place? So the steel erection crew learned a lot by practicing on this mock-up. Also the welding in the field. And then finally, of course, we did the proper shop drawings to ensure that all of the parts and pieces were properly detailed. Here you see, in addition to the panel with the door opening through it, you'll notice the ledger angle for the deck that will be supported by the core wall and the shear tabs for the beams that will be supported by the core wall. These were all prefabricated, so as they came to site, there was nothing to add. The wall panel went up and the beam was connected. It was very, very fast because of this. In addition, all the mechanical penetrations were pre-planned, prefabricated as part of the panels. The panels were made and stockpiled in the yard, put on the truck, and then shipped to the site where they were hoisted by the crane and then erected down into, in this case, the foundation, which was a mat foundation. And the bottom of the core was supported on these stanchions that were embedded in the mat foundation, which was a 3.5 meter thick mat. Here you see that construction sequence, the 2-story tall columns, the single-story wall panel being inserted. And if you look in the column, you'll see a circular hole. And that circular hole is the placing port where the concrete pump was placed in order to pump the concrete into the wall later. Here you see the erection. Interestingly, this building was built immediately adjacent to my personal office. So each day I came to my office and looked out the window. This is the view from my window. I took this picture personally from my office. So it was this close to me each day as I watched this building build.